sir. Today I am presenting experiment number 3, sampling, aliasing and reconstruction. The main objective of this experiment are to verify the sampling theorem, observe effect of aliasing, reconstruct a sample signal using sinc interpolation, and compare the original and reconstructed signal in both the time and frequency domain. I am using Python, Google Colab for Jupyter. Here's the formula. Xt equals to sine 2 pi f1t plus 0.5 sine 2 pi f2t. Here f1 equals to 10 hertz and f2 is 30 hertz. Here is the f2 is the maximum frequency. So Nyquist is 2 into f2, 60 hertz. I take here 3 frequency which is 30, which is maximum, minimum and Nyquist, where the first case uses 80 hertz, second case uses 60 hertz, and third is 45 hertz. 80 hertz is above the Nyquist, 60 hertz is Nyquist, and the 45 hertz is in below the Nyquist. Above the Nyquist, here's the frequency. Above the Nyquist 60 hertz, so 80 hertz is greater than 60 hertz. Therefore, according to the sampling theorem, aliasing should not occur. Now, looking the graph, the blue curve represents the original signal. Blue curve original signal. The point represents the actual samples, and the dashed curve represents the signal constructed using sinc interpolation. We can see that the reconstructed waveform closely follows the original waveform. Here you can see the both and compare. A small reconstruction error can still occur because this is numerical simulation with a finite time interval and a finite number of samples. Case 2 at Nyquist. Let's move the second case. Here is 16 hertz equals to Nyquist. Therefore, highest frequency is 30 hertz is being sampled in the minimum frequency. Theoretical rate required as reconstruction. According to theory, reconstruction is possible. However, 30 hertz component is sampled at only 2 samples per cycle. So this case can be more sensitive to the sampling phase and the finite duration of our simulation. When we compare the original and reconstructed signal, we can observe the practical reconstruction behavior. The result is broader consistent with sampling theorem with any small discrepancy mainly coming from the numerical implementation. Below Nyquist aliasing, here is the 45 hertz below interpolation below Nyquist. The general formula is aliased frequency equal to the absolute value of original frequency minus k times of sampling frequency. For the 30 hertz component, we can take k equals to 1. So, yeah, aliased frequency equal to the absolute value of 30 minus 45 is 15 hertz. This is most important validation of this experiment. Now, if we look at the magnitude spectrum, we can observe the effect of aliasing. The 30 Hz component has folded into the frequency range below the Nyquist frequency and appears 15 Hz. Therefore, our simulation agrees with the manual calculated aliased frequency. Here is a reconstruction error. A reconstruction at first we can say sinc reconstruction. Now let's discuss the reconstruction process. I have used a sinc interpolation to reconstruct the signal from its samples. In simple terms, sinc interpolation takes every sample and place sinc shaped function around it. Then all these sinc functions are added together to reconstruct the continuous time waveform. When the sample frequency satisfies the sampling theorem, the process can recover the original signal accurately. However, there is an important point. If aliasing has already occurred, sinc interpolation cannot remove it. This is because aliasing causes information to the lost during the sampling process. Reconstruction error and spectrum. The error is simply original signal minus reconstructed signal. Original signal minus reconstructed signal. The RMSE or root mean square error. RMSE equal to the square root of the average of the squared difference between the original and reconstructed signal. A smaller RMSE means the reconstruction is closer to the original signal. We also compare the magnitude spectra. Uh, this is my presentation for today. Thank you, sir.